Let's have a look at the answers to last year's probability questions, last year being 2014, the end of year exam. So question 18 is the first one, and this is in the non-calculator section. For each of the following scenarios, state whether or not X describes a discrete random variable. Circle your choice, there's no need to justify your answer. So first one, A, X is the number of hearts in a standard pack of cards. So there's nothing being drawn out there, it's not mentioning drawing out cards or anything, it's just saying X is the number of hearts. Now that's not a variable because we know that in a standard pack of cards, a quarter of the cards are hearts, so that's 13, so there's no variable there, it's a known thing, so it's a no. Second one, X is the number rolled on a single roll of a standard die. That's an experiment, the outcome is unknown, so it's a variable, and it's either the number is either going to be 1, 2, 3, 4, 5 or 6. So it's indeed a random variable, discrete random variable. X is the number of times a 6 is rolled after 20 rolls of a standard die. That's also a yes in that situation as well for similar reasons. X is the amount of time that a particular student is late to an exam. We've got measurement happening there. Time is measured, therefore it's a continuous random variable and not discrete, so the answer is no. Okay, 7 standard dice are rolled. Write down the expression for the probability that at least one die shows a 6. So notice this is a non-calculator, so it's using language such as write down an expression, so we don't actually have to solve it. And we use our formula here, NCX, P to the power of X, Q to the power of N minus X. And 7 standard dice are rolled, and the probability of getting at least 1 6, so the probability of success is 1 on 6, the probability of failure therefore is 5 on 6. Now if we look here at this scenario, we've seen this before. Write down an expression for the probability that at least one die shows a 6. Okay, so at least one could be the probability of 1 or 2 or 3 or 5, 6 all added together, but we know that that at least one die statement, look at that there, that at least one die statement here means 1 minus the probability of there being no die showing a 6. Okay, no die showing a 6. So that at least one scenario is equivalent to 1 minus there being none. Okay, so what I've done here is looked at that situation. I've got 1 minus, and I've put in the correct values in the formula for getting no 6s out of those 7 rolls of the die, and you can see there I've used that formula there and put the values in, and 7C0, remember, is 1, anything to the power of 0 is 1, so all that remains is 5 on 6 to the power of 7. You can see that there, and that's as far as you have to go. Next question, I have 3 coins, each with a number on each side. The first coin has a 0 and a 2, the second coin has a 0 and a 3, the third coin has a 0 and a 4. And in an experiment, all 3 are flipped together. So the sample space for the experiment, you can see here the first coin can either be 0 and 2, the second coin can either be 0 and 3, and the third coin can be either 0 or 4. So we end up with this tree diagram type situation here, with 8 different outcomes. Just have a quick look at that, pause the video if you need to, and have a look at the outcomes. Okay, so the tree diagram is a good one for this one. And notice I've preempted something here and looked at the next question. I've actually worked out a thing called the difference here, but we'll get back to that in a sec. But the sample space is simply that tree diagram there. Alright, let X be the difference between the highest value and the lowest value shown on the 3 coins. Complete the probability table for X. So in each case, in each part of the sample space, you're looking for the difference between the highest and lowest coin. That's pretty easy to work out. 0 there, it's 4 in the next one, and so on. And you can see the different values going down the table, top to bottom. Alright, so 0, there's only a 1 in 8 chance of the difference being 0. There's no chance of the difference being 1, so you can see how I'm getting these figures here. Let's use that instead. So we can see how I'm getting 0 there. There's no possibility of the difference being 1. As far as the difference being 2 is concerned, there are 2 outcomes that give me that out of the 8, there and there. 2 out of 8 gives me 1 in 4. There. Same with 3, the difference 3. There's a couple of ways in which I can get that there and there. So that's 2 out of 8, which is 1 out of 4 chance. And difference of 4, there are 3 different scenarios where I can get a difference of 4 out of the 8. So 3 in 8 chance of that. So that's how I get my table there. Below is, x is a random variable. Below is the graph of the probability of x equaling a certain value. Okay, so you can see the probabilities are pretty variable here. We've got a 0.2 there, 0.1 there, another 0.2, a 0.4 and a 0.1. So you can see the different probabilities there. And it's asking you to convert that to the graph of the probability of x being less than and equal to x. Okay, so obviously for the value of 1 here, it's the same because that's the first value. So the probability of it being 1 is 0.2, and there's nothing less than 1, so the probability of being less than and equal to 1 is the same, so it's still 0.2. Now, the next one you'll notice, if I look at the answer, is 0.3. Now, how do you get that? Because you add its probability of it being 2 or less, including 2, so you add these two probabilities together, the 0.2 and the 0.1, and you get that value there of 0.3. Okay, here's some of these boxes. Next one, probability of it being greater than or equal to 3. Okay, so this time we add these 3 together, 0.2 plus 0.1 plus 0.2, giving us 0.5. You can see that the value there is 0.5. And so on. We keep on adding up the previous values, so probability of being less than or equal to 4. You can see these 4 values here have been added up, 0.4 plus 0.2 plus 0.1 plus 0.2 to give you 0.9. And the last one, you add them all together, and you get the probability of 1 there, because they're all previous results are added together. Okay, in now to the calculator section. The lengths of fish in my local lake are normally distributed with a mean length of 24 and a standard deviation of 3. Determine the probability that a fish caught is 30 centimetres or longer. Alright, so always good, as you can see here. I've set up our normal distribution curve. There it is, with 24 in the middle because that's the mean, and 30 to its right. And we're looking at the probability that's 30 or greater. So we're looking for this area to the right of 30. In fact, we could probably shade that in here. And the yellow, that's the area we're looking for there. So it's normal CDF, 30 being the mean. Sorry, not 30 being the mean. 30 being the lower bound, infinity being the mean. Sorry, infinity being the upper bound. 24 being the mean, got there eventually, and 3 being the standard deviation. So we put those into our calculator, and our answer is 0.02275 or 0.228 to 4 decimal places. Very important to set that out as I've done there. Draw the diagram so the person marking the question can see what you're doing. When fishing in the lake, I caught 4 fish. Using your value from part A, determine the probability that one of them was longer than 30 centimetres and 3 were shorter. Okay, so we've got a binomially distributed variable here with a probability of success, that is, it's longer than 30. We've already calculated from the previous question. You can see that's been transferred to there. And my number of trials is 4. So that's the scenario there. Probability of x equaling 1. So we're looking at one of them being longer than 30 centimetres. So it's binomial PDF. We're only after one value. So it is, binomial PDF. 4 trials, probability of success 0.02275, comma 1. That's the one we're after. And the answer is 0.0849. 10 sheep. 4 black sheep and 6 white sheep are herded into random into 2 different fields. 5 sheep per field. What is the probability that 2 sheep will go into each field? Okay, so now, interesting situation here because there's only 4 black sheep. So obviously if there's 2 fields, here and here, then if 2 black sheep in this field here, then the other 2 must be in the other field. Okay, there's no third option. So really we're looking at 2 black sheep being in one field will give us our answer, because by default the other 2 will be in the other one. So you can see here I've set out my variables, my values here for hypergeometric. Total population is 10. Number of successes, that is black sheep, is 4. Number in the sample is 5 per field, and what we're after is 2. So it's a good idea still. Of course, you can put this in the calculator, but to put it in the formula like I have, put in the correct values, and then use your hypergeometric program. There it is, and 0.4762 is the answer. Next one, all the black sheep will go into the same field. This one we've got to consider 2 different possibilities. That is, the 5 black sheep could go into this field. So try and get the black sheep happening here, or that they could go in the other field. So notice here I've got 2 different results. I've got the probability that there'll be 5 sheep in the first field, and then the probability that there'll be 5 sheep in the black sheep in the other field. Okay, so I've got 2 different situations here. Now I didn't have 2 different situations the first one, because if there was 2 in one field, there had to be 2 into the other. Okay, so there was no sort of doubling up. But here, there's 2 scenarios. There could be 5 in one field or 5 in the other. So that's why I've got 2 different answers here. Notice my values here are very similar. The x value is now 4. That's the only thing that really changes. But I've got to look at both fields. So that's why I've doubled the answer and get 0.0476. Okay, when picking apples, a farmer noticed that 15% of apples are 5 centimetres or smaller in diameter, and 30% of apples are 8 centimetres or more in diameter. Determine the mean and standard deviation of the diameter of the apples, assuming that the diameter of the apples is normally distributed. Okay, so here it's one of those simultaneous equation situations, and you'll notice I've got the we've talked before about getting 2 graphs set up, the actual situation. And we've got the 2 areas shaded with the probabilities there, 0.1500 and 0.3600. You don't really have to put the 0 on the end, but you can if you wish. And then we've got our Z situation down below that mirrors it. Remember, to find our Z values, we use the standard normal distribution. And you can see I've done it there using inverse normal, being careful with the right-hand one, because it's always the less than. So notice how it's 0.3000 there, but when you find out the Z score, you must use 0.7000 because it's always the less than value when you're using inverse normal. And by the way, that should be inverse normal there as well. Just pointing that out. Let's see if I can get that in there. So inverse normal there as well. Then you get your 2 Z scores, here and here, and you use the Z equation here. Z equals x minus mean over standard deviation. We use that in 2 scenarios. Notice here, because it's a calculator section, the workings there, you can solve these 2 equations simultaneously on the calculator, and it saves a lot of time doing that. Especially with those sort of figures where they're not, you could do it, put other steps in, but what's written there, as you can see, is more than adequate for answering this question. And you get eventually you get your mean of 6.9921, and I've cut off the standard deviation there. You might be able to work that out yourself. But anyway, you can see the general method there to work that out. Box contains 100 marbles, of which 50 are yellow and 50 are green. A marble is drawn and its colour is recorded, then put back in the box. This is repeated until 20 marbles have been drawn and their colours recorded. What's the probability of getting an equal number of yellow and green marbles? Okay, so there's 20 trials. Probability of success is 0.5, hence failure is 0.5. And we're looking at, if you get equal ones, obviously if 20 are drawn out, you're going to get 10 yellow and 10 green. So that's how we got our binomial PDF here, like so, and the answer is 0.1762. That should be an easy mark for most people there. Explain why the probability of getting more yellow marbles than green marbles is exactly the same as getting fewer yellow marbles than green marbles. Okay, so you've got to get your head around this one. So if you're getting more yellow than green, okay, what it's saying here is that's exactly the same as probability of getting fewer yellow than green. So if you're getting fewer yellow, you're getting more green than yellow. So basically it's saying that the probability of getting more yellow than green is the same as the probability of getting more green than yellow, or vice versa. The probability of getting fewer green than yellow is the same as the probability of getting fewer yellow than green. And the latter one is what I've settled on here, because we know that P equals Q equals a half. So P and Q are the same. So if we look at the situation here, that would be how we would work out the probability of there being fewer yellow than green, okay? And because if there's fewer yellow, it means there's going to be 0, 1, 2, 3, all the way up to 9 yellow. And you'd put those in that equation and add all the results up, okay? Now, as soon as you change it the other way, okay, then all that changes over is Q becomes P and P becomes Q, because if yellow is your success and green is your failure, and you swap that around, then green becomes success and yellow becomes the failure. Then because they're both 1/2, the figures are exactly the same. So if I was going to work out the opposite result, it's exactly the same, because P and Q equal a half, and that's the whole gist of this question. So not exactly what would require the whole setting out for that, but something such as that the results would be identical. Using your answers to part A and B, determine the probability of getting fewer yellow than green marbles. Okay, so we know that getting fewer yellow, that is 0 to 9 yellow, is the same as getting fewer green, which means 9 to 11 to 20 yellow. They're the same result. Okay. We also know our result for getting 10, which is part A of the question. So there's only 3 scenarios here. You're either going to get 0 to 9 yellow, excuse me, you're going to get 10 yellow, or you're going to get 11 to 20 yellow. So because these two are the same here, what you're going to get is the probability of 0 to 9 yellow is going to be 1 minus that probability of getting 10 divided by 2. Because if you line up all the results, 1, 2, 3, 4, 5, there's a number of yellows, 7, 8, 9, 10, sits out on its own, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, we've already established that this is the same as this. Okay, so and all 3 of those, if I put a bracket around, all 3 of those equal 1. So to work out this one here, it's going to be 1 minus the probability of 10 divided by 2. And that's how you get this result here. And that's what I've done. And we've incorporated our answer to part A there. It's 1 minus 0.1762 over 2 and equals 0.4119. Okay, so they were the answers to last year's probability, which probably wasn't too bad last year, a few little tricky things, but by and large, pretty accessible to most people. Hope that helps.